Moving on to the fourth exercise, we want to integrate from 0 to 7 square root of 4 plus 3x. As usual, well, first we need to verify that we have a continuous function on the interval, but there is no problem because for this function to be defined and continuous, we just need 4 plus 3x to be at least 0, and that is true certainly if x is positive. So we look at the composite part, we plug 4 plus 3x inside the square root function. So we're going to take for the new variable u 4 plus 3x. Then du is 3dx. What we have in the integral is just dx, so we solve for dx, we get that dx is 1/3 of du. So we're going to get square root of u multiplied by 1/3 du. In other words, 1/3 integral of root u du. That's for the indefinite integral. To interpret this in terms of the definite integral, when we add these bounds of integration, so x varies from 0 to 7. In terms of u, what that means is when x is 0, I plug x equals 0 in the expression for u, I get 4 plus 3 times 0, so 4 is a lower bound of integration. On the other end, when I plug x equals 7 in the expression for u, I get 4 plus 3 times 7, that's 21 plus 4, 25. So that's my upper bound of integration. Square root of u is a continuous function between 4 and 25. So according to the Fundamental Theorem of Calculus, the integral on the right-hand side is simply an antiderivative of square root of u evaluated between 4 and 25. Root u is just u to the 1/2, so an antiderivative is 2/3 u to the 3/2. So we get 1/3 multiplied by 2/3, and then we have u to the 3/2 evaluated between 4 and 25. And 25 to the 3/2 is 125 because this is 25 to the 1/2, which is 5, that you cube, which gives you 125. On the other end, 4 to the 3/2, it's 4 to the 1/2, that's 2, that you cubed, gives you 8. So we get 2/9 of 117. 117 over 9 is 13. You multiply by 2, we get 26, sorry. So to conclude with these examples of definite integral, we're going to look at a slightly trickier one. We want to calculate the integral from 0 to 4 of x over root of 1 plus 2x. First thing we need to check is that we're going to be able to use the Fundamental Theorem of Calculus. In other words, that the function x over root of 1 plus 2x is continuous on the interval from 0 to 4. The only problem would be if 1 plus 2x is not strictly positive. But 1 plus 2x is positive as long as x is greater than negative 1/2. And so this is the case for any x in the interval 0, 4. So we have no problem. We're going to be able to use the Fundamental Theorem of Calculus. So we try to proceed as usual. Focus on the composite part. We have 1 plus 2x that is plugged into 1 over root x. So we take for u 1 plus 2x, and therefore du is 2dx. Now here we see that we have an unusual situation because this 2dx, what remains in the integral after we take care of the composite part, is not just a constant multiple of du. We have this dx that we're going to be able to express in terms of du, it's 1/2 du, but there is also this x here, and it is not clear what to do with it. Fortunately, x can be expressed in terms of u rather easily, as you can see from the expression of u. U is 1 plus 2x, we can easily solve in terms of x, so that this x in yellow in the integral can be replaced by something in terms of u, and this way we can obtain an integral that depends entirely on u. We cannot have an integral with some x's and some u's. We need everything in terms of the variable u. So if I solve for x, I get that x is u minus 1 divided by 2. Therefore, in my integral, I'm going to replace x by u minus 1 divided by 2. Square root of 1 plus 2x is square root of u. and dx is 1/2 du. Pulling out the 1/2 out of the u minus 1/2 and the 1/2 out of the 1/2 du, I get 1/2 times 1/2, 1/4 that I can pull out. Well, before I should talk about the bounds of integration. We have an integral from 0 to 4, that is x varies from 0 to 4. What that means for u is that when x is 0, u is 1, because if I plug 0 in the expression for u, I get 1 plus 2 times 0. So the lower bound of integration is 1. When x is 4, u is 9, because 1 plus 2 times 4 is 9. And as I said, now I can pull out 1/4. So I get 1/4 integral from 1 to 9 of u minus 1/√u. So we have transformed integral of x over root of 1 plus 2x into an integral of u minus 1/√u. It might not be transparent that this is much better, but in fact it is, because now I can rewrite u minus 1/√u by bringing up this 1/√u, and instead of dividing by √u, I'm going to multiply the top by u to the negative 1/2. And now I can multiply things through. I have u to the 1 that I multiply by u to the negative 1/2 gives me u to the 1 minus 1/2, u to the 1/2. And then negative 1 times u to the negative 1/2 gives me negative u to the negative 1/2. Now that I have rewritten the integral under this form, we can obtain an antiderivative. Both functions u to the 1/2 and u to the negative 1/2 are continuous on the interval from 1 to 9, so we can use the fundamental theorem of calculus. All we need is an antiderivative of the function we integrate. Antiderivative of u to the 1/2 is u to the 1/2 plus 1 3/2 divided by 3/2, so in other words 2/3 u to the 3/2. And an antiderivative of u to the negative 1/2 is u to the negative 1/2 plus 1, that's u to the 1/2, that you divide by 1/2, so that means you get 2u to the 1/2. Now if we plug values in, 9 to the 3/2 is 9 to the 1/2, that's 3, that you cube, you get 27, but this 27 divided by 3 is going to be 9 times 2, 18. And then 9 to the 1/2 is 3, that you multiply by 2 is 6, so we have this 18 minus 6, 12 for the value of what's in the bracket at 9. The value at 1 is 2/3 minus 2. So once we simplify all that, we obtain 10/3. So now we're going to turn to the next video for a last set of properties of integrals that we're going to prove using substitution.